Hello.
Cognition critical.
Boy, it's sure pretty warm in here.
Temperature critical.
That was strong.
Temperature low.
Let's talk about getting water. The approach every beginner knows is to just use an ice crusher. So you stuff in the ice, and then you wait, and then you wait some more, and you wait further. More waiting. Huh. So we've gotten some water, but still half the stack is here, and it took a long time, and took a lot of electricity actually. It says 10 watts here, but that's only the base electricity usage. I think it's about 1000 when it really heats things up. Down here in the logic value section we can see setting, and the setting value is actually set to 15 degrees Celsius. What if we change that with a logic writer? Ice crusher? Setting. In value is the logic memory, and the logic memory is just 0. So we're aiming for 0 Kelvin, because the value is being given to the device in Kelvin. You can see that here in the configuration cartridge tablet. 288.15. 273.15 is 0 Celsius. Now if we add 15, we arrive here. Yeah, that's the setting. Now let's change that. Now the setting is 1, because it doesn't accept a 0. How fast is it now? Faster. Let's try again with a full stack. Very fast now. Again, all it took was the logic writer setting the output to the ice crusher. You can see that here in the tooltip. The variable that we want to write is setting, and this thing needs a value that it wants to write in the in selection. Here we selected the logic memory, so just place a logic memory chip without adjusting it in any way. That gets the problem solved. But there's other, even simpler ways to get drinkable water. In episode 3 at the furnace I showed you quickly the kit liquid drain. It has the passive liquid drain for gas pipes, which will leak out all liquids that may be in there, not at super speed but fast enough. If you need it faster, use multiple. Or is it multiple? Then there's the active liquid outlet for liquid pipes. You turn it on when it's powered and it will pump out all the liquid into the atmosphere. And this, the passive liquid inlet, is the exact opposite. It doesn't need any power and it will get all the liquids from the atmosphere. Passive liquid inlet. Wait, does that mean... Why, yes, it does. Now that's simple. Clean drinking water, right from the air.
Toxin critical.
It's a bit of a problem though if the room is polluted, because that also gets into the pipes. I mean, whoops, that doesn't work.
Toxin critical.
Never forget to flush, real life advice. So this setup is nice, easy, but there's a better one. Oh, there's pollutant in there? Honestly, I didn't expect this. This is a liquid one-way valve and the pollutant is not liquid. Why is there pollutant in there? Anyway, there's the third alternative though that a very nice guy on YouTube showed me. I tried it today and yep, it actually works. you have an evaporation valve, which leads into a gas pipe, of course, because that's the way it works. Then from there, a condensation valve, and that leads to the actual container. Still plenty of pollutant in the room, so let's see how this works. Oh, we don't have any more ice in the room. There, water. And in here, only water. The pollutant is not getting in. Polluted, polluted, not polluted. So you can take your regular kit valve, scroll a little, then we get the expansion valve. And then the next one is the condensation valve. Turn both of them open, and then this works. So what about these two then? Well, since the gas is getting in there, we can also get it out with the crusher, with the scrubber. See, it's reducing. In this tank, in this liquid tank, the pollutant is reducing now. Here also? No, because we had a one-way liquid valve. I still don't get how the pollutant got in there. I used this months ago. Maybe they changed the calculations, or maybe the circumstances here are somehow different. Anyway, this is one way to do it, but this way seems much more elegant. And it saves to the crusher. And the logic chip. Oh, which you can turn off, by the way. Once the value is set, it is set. But you don't actually need a scrubber to get rid of the pollutant. And the filter will be used up over time, right? Remember the phase change diagram of pollutant? Between minus 90-ish and plus 150-ish degrees Celsius, as long as we get the pressure a few megapascals high, it will be liquid. And there is the passive liquid drain. Wait, does this mean all we need is a high pressure pipe and it will leak? Yes, 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 that's what it means. Mind the ratio. It is going down. And here in the pipe we can see it is being liquefied by the pressure. And the passive liquid drain then lets it seep out of the station. 5 minutes later. Man, this is really slow. And if we spray paint a little, well, it's not that bad.
Cognition critical.
Still going on. Huh.
Toxin critical. Toxin critical.
What if we give this thing much more volume? Does it help maybe? Will take a while. Ah, now it's getting liquid. Okay. This of course lowers the pressure in the room somewhat. So, ratio in the room, 56%. Wow. I guess I made the volume too big. Because this thing will only release once we have 45,000. But I can lower it. Crazy! Certainly losing pollutant into the lunar atmosphere. Whoa. Dude, we're about 2 minutes into this experiment. Maybe 2 minutes, not more. The pollutant is gone. That was so ridiculously much, but none is left. No pollutant is left.
Temperature high.
Bit hot though. Why is it this hot? Oh, right. That must have been the pollutant condensated. See, when gas turns liquid, then this increases heat. And when it turns from liquid to gas, then it decreases heat. Lots of pollutant was heated up by compressing it from the gaseous form into the liquid form, and so that must have heated up the room. How do we get this small room a little bit colder? Look here, I placed some liquid pipes, could also have used gas pipes, depends on what medium we want to use. They are evacuated, there's nothing in there, and these are convection radiators. Part of the same kit is also the radiation radiator, not useful here where we have atmosphere. Oh. The room is already cooling down, even though these are still evacuated. I guess it's all the water that we have here in our tanks. We can see minus 53 joules convected, meaning this thing is not shedding heat, it is gaining heat. You can see also temperature just rose by 1/100th of degrees Celsius. I will remove those so that we can make the heating experiment. There. Nothing's disturbing our nice experiment anymore. Okay, let's start it then. Tablet docks are nice. This is outside, and well, it's a bit weird. This is showing us the inside value because the table is kinda in that room. The other tablet on the same table also shows us the same value. What, you can't see that? No. 123, 53.3. Out here we have 113 and 37. So let's look at this experimental setup. Here we have a little room, 1, 2, 3, 4, 5 fields big. Now while the airlock is in this state, we have 1, 2, 3, 4, 5, same size. How many radiators?
Temperature high.
1, 2, 3, 4, 5, 6, 7, same on the other side, and between I have insulated pipes. So the experiment is kind of balanced. Here we have 50 degrees, bit hot, and here we have 63 degrees. Now, what happens if we fill that pipe with water? There, 360 or 380 liters, 20 degrees Celsius. Now, water is pretty solid, so to speak. See, it's heating up from the rooms because from both sides it's being heated, but the rooms are also dipping down in temperature a lot. So the rooms are being cooled by the water is being heated by the rooms, but the water doesn't care much. It is basically, has a lot of mass, it's very inert. So that would mean if the goal was to equalize both rooms, for example, if this room, if the large hall hidden behind this wall here would have its own cooling solution, and we don't want to implement an additional cooling solution for that room, and so we just want to make sure that this room's temperature and that room's temperature is kind of connected, then we shouldn't use water. The water itself is just too inert for this. So what if we use pollutant in these pipes then? I've reset the experiment, 64 degrees, 51 degrees. Okay, 4 megapascals of pollutant. This room is heating up actually. Interesting. What are both rooms doing? The right one is getting colder and this one is getting hotter. Interestingly, the pollutant that I added here to this pipe had 20 degrees, but now it pretty instantly rose like this in temperature. So this means if you want to equalize both rooms temperature-wise, pollutant is a great way to do that. Let's see how fast we can bring down the temperature of the other room if this one is pretty cold. Almost equalized. So again, I started with almost 0 degrees oxygen in here. On the other side was at 58 degrees Celsius, and now it's equalizing pretty quickly. I mean, look at this speed. So if you want to connect the temperature of two rooms, a liquid pipe with some radiators and pollutant is a pretty good solution. Wonder if nitrous oxide is in any way different. Let's try that. Starting situation. Evacuated pipe.
Temperature high.
Huh. Why is the pressure decreasing so rapidly?
Airtight critical.
What? So I added some more of that stuff, and I guess the problem is I added it in the form of gas, and the pressure compresses it so much that it becomes liquid, and when it becomes liquid, it heats up. Pretty hot in here. Yep. That's
Temperature critical.
not quite the experiment I wanted to do.
Temperature high.
Another injection. Wow, still getting hotter. You know what? Let's evacuate this room here and fill it with really, really, really cold oxygen. Yep. Yeah, all that condensation heated up the material extremely. Both rooms are now almost equally hot. So again, this room, I will evacuate it and fill it with hot oxygen, with very cold oxygen. Okay, minus 100 degrees Celsius oxygen. 100 kilopascals. What's happening? Yeah, cooling down a lot. We have to remember it's not just cooling down the other room, but also the very hot pipe. Dum-da-dum. The assumption is safe that the temperature of the pipe will be somewhere in between these two. And there it is, 45 degrees. Interesting that the pipe's temperature is decreasing. Shouldn't it like be exactly constant, or what's happening? Oh, it of course depends on the pressure in the respective rooms. Oh, this one, yeah, this one has much higher pressure, so it has more, well, more voice when it comes to voting for the temperature. And this one's colder. That's why this one is also getting colder. Makes sense. Another go. Okay, vacuum. 42 degrees, 44 degrees. I wonder if that's too cold. Minus 70-ish degrees is what I chose. $16 and falling, because the pressure in here is indeed once again higher.
Temperature low.
Shut up, it's not low. Yeah, nothing much happening at this point. I think that using pollutant is indeed the best choice for these purposes, because we can look at some numbers. Here, water. The specific heat is 72 joules per Kelvin, per kilogram. Honestly, I don't know what this means, but it's 72. Now, let's go for nitrous oxide. $37.2. I would think that it is about like the heat inertia that this thing has, how much heat it carries itself. Currently, it's just pollutant is better for communicating heat, and water is better for holding heat, and nitrous oxide is somewhere in between. Anyway, that's enough of that. I think it has been long enough. See ya. La 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 la.
Cognition critical.
Oh.
Health critical.